Hello, welcome to the second video in energy and work. This time we're going to learn about work. So, now remember that we're dealing with physics, so our definitions of some of the words that we use will have to change to incorporate the understanding of physics. And so when we say work in physics is defined as the product of the force and the distance moved in the direction of an applied force. Got that? So it's the product of the force and the distance moved in the direction of the applied force. So this force is causing something to move, and therefore we have work. So here we have someone pushing a table. This is the applied force. This is the mass. This would be the force friction. We're going from zero velocity to having a velocity, and we're moving it from that distance to that distance. Therefore, according to this definition, work equals force times displacement, or as you'll see on your information sheet, W equals Fs, where W is the work and its unit is joules because it's a form of energy. And then we have force times displacement. Let's do an example. Here we have a book resting on a tabletop. We have a force that's applied 1 Newton. It's applied constantly, causes the book to move 2 meters. Calculate the work done when a horizontal force of 1 Newton is used to push a book a distance of 2 meters along a desk. W equals Fs. 1 Newton times by 2 meters equals 2 joules. That's the amount of work. And remember, work is a form of energy, so it's in joules. That's how much energy you're using doing that work. No work is done if there's no movement. Now this can confuse students a little bit, so we'll have a couple of examples. For example, if you hold a textbook in your hand and the textbook isn't moving, in physics no work is being done. But if I asked you to hold that textbook there for an hour, it would feel like you're doing a lot of work because you'd actually get fatigued. But in terms of physics, you're not doing any work because the weight force is being balanced by the lift or the force that your hand is applying. And so because that's an action-reaction setup, there's no applied force, there's no net force causing any motion. Another one that confuses students is a helicopter. Now if a helicopter is hovering, you think, well, there's a lot of work being done. The engine's using a lot of fuel, the rotor blades are going around, a lot of noise is being created. But in terms of physics and in terms of the helicopter, if the helicopter is hovering, there's no applied force because all the forces are balanced. The weight force is balanced by the lift from the rotary blades, so no work is done. If it moves up and down though, work is being done. And if we break it into little systems, there's work happening within the system. But if we look at the helicopter as a whole, no work is being done. And another one, if you push against a wall, if I asked you to push against a wall as hard as you can for as long as you could, you'd probably do it for 10-15 minutes and then give up because you're tired. Feels like you've done a lot of work. But in terms of physics, unless that wall moves, no work is being done because you've got to have some displacement, and there's no displacement happening. Alright, now we can show the applied force on a force displacement graph. And if we have a force displacement graph, the work is the area under the graph. And so here we have force applied, it's 150 newtons east, and the displacement is 100 meters, so W equals Fs, so F times S, so it's the area under the graph. That would be our work done. In this case, it's 15,000 joules. Remembering our standard units, newtons, meters gives us joules. We can deal with slightly different shapes, so the force applied doesn't have to be constant. Usually most of our questions it is, but in a graph question it doesn't have to be. Again, we would just work out the area under this graph. and we divide and conquer into shapes so that we could work out this shaded area. And so this time they did 100 by 100, so they did this rectangle here, and then they did a rectangle 60 by 100, so that's that rectangle there, and then they halved it to get the triangle, and they got 13,000 joules. So you have this question in your booklet, have a go at it. A car is pulling a loaded trailer in an easterly direction along a horizontal road, constant force, calculate the work done. There you go. Now, lifting things is a particular example of work. When calculating the work done in lifting an object vertically, that sounds better, the force applied will be equal to the object's weight. Now, we always will be assuming that we're lifting it at constant speed. Okay, so we're moving it up at constant speed, that's the work that we're doing, so the applied force must equal the weight force. Now this is different from if we're just holding something, where the applied force is equal to the weight force, but there's no distance, so we're not having any work done because it's not moving a distance. So calculate the work done by lifting a 15 kilogram school bag at a constant speed from the floor to a port rack. Now a port rack is like a bag rack, but in Queensland they call school bags ports, because suitcases used to be called ports, and that's why you have porters who carry things at railway stations and boats in the old movies, and why you have, when you have to go round a rapid, it's called portage, when you carry all the stuff, because that's what they used to do, carry the ports around the rapids when they're trying to go up rivers in Africa. Whatever, I digress. So we've got our mass and we've got our distance, and so we would calculate the weight force. So weight force equals mass times gravity. They're using 10, we would use 9.8, so that's the weight force. That's what we're countering when we're lifting something up at a constant velocity. So that would be our applied force, and the 1.8 meters gives us 270 joules. How much work is done by Jackson in climbing a 3-meter slippery slide ladder at constant speed if he has a mass of 90 kilograms? Well, in climbing a ladder, Jackson exerts a force equal to his weight. So he's not accelerating, but he's moving at a constant velocity, so the force is equal to his weight, and so we would just work out his weight force. 90 times 9.8 is 882 newtons. S is 3 meters. Put it into W equals Fs. They've got a cos theta here that we don't worry about because it's always going to be 0. Sometimes people would put a sine theta there, in which case the angle would be 90, and that would be 1. So this would be 1 as well. And so we get the answer, just W equals Fs, 2,646 joules. That's how much work is done going up the slippery slide. So you should be able to have a go at these questions here in your workbook. Slightly different ones, and then different. Remember, this is a force displacement graph, so you can work out the work done there. And you will also have, following these ones in your workbook, a whole lot of questions called work and energy questions that you can do. Next video we'll be looking at kinetic energy, which some of you may have already heard of and done a little bit of, but we'll be doing some more of it. See ya.